Hello. Please hit like button and subscribe my channel. Also press bell icon for future video notifications. Thanks.
From atomic clocks to secure communication to quantum computers, these developments are based on the increasingly better control of the quantum behavior of electrons in atomic shells with the help of laser light. Now, for the first time, physicists at the Max Planck Institute for Nuclear Physics in Heidelberg have succeeded in precisely controlling quantum jumps. Compared with electron systems, nuclear quantum jumps are extreme, with energies up to millions of times higher and incredibly short zeptosecond processes. The experiment required a sophisticated X-ray flash facility developed by a Heidelberg group led by Jörg Evers as part of an international collaboration. One of the great successes of modern physics is the increasingly precise control of dynamic quantum processes. It enables a deeper understanding of the quantum world with all its oddities and is also a driving force of new quantum technologies. But from the perspective of the atoms, coherent control has so far remained superficial. It is the quantum jump of the electrons in the outer shell of the atoms that has become increasingly controllable by lasers. Energy-rich quantum jumps for nuclear batteries. In addition to this analogy to electron shells, there are huge differences, explains the director at the Max Planck Institute for Nuclear Physics in Heidelberg. They've got us so excited. Quantum jumps between different quantum states are actual. And the energies of these quantum jumps are often 6 orders of magnitude greater than in the electron shell, says Keitel. A single quantum jump made by a nuclear component can thus pump up to 1,000,000 times more energy into it, or get it out again. This has given rise to the idea of nuclear batteries with an unprecedented storage capacity. Such technical applications are still visions of the future. At the moment, research entails addressing and controlling these quantum jumps in a targeted manner. This requires precisely controlled, high-energy X-ray light. The Heidelberg team has been working on such an compared with the electronic quantum jumps, they are much more sharply defined. Because this translates directly into more accurate frequencies according to the laws of physics, they can, in principle, be used for extremely precise measurements. For example, this could enable the development of ultra-precise nuclear clocks that would make today. In addition to technical applications of such clocks, e.g., in navigation, they could be used to examine the fundamentals of today's physics much more precisely. This includes the fundamental question of whether the constants of nature really are constant. However, such precision techniques require the control of quantum transitions in the nuclei. Coordinated light flashes enhance or reduce the excitation. The principle of the Heidelberg experimental technique sounds quite simple at first. It uses pulses, flashes, of high-energy X-ray light, which are currently provided by the European Synchrotron radiation source ESRF in Grenoble. The experiment splits these X-ray pulses in a first sample in such a way that a second pulse follows behind the rest of the first pulse with a time delay. One after the other, both encounter a second sample, the actual object of investigation. The first pulse is very brief and contains a broad mix of frequencies. Like a shotgun blast, it stimulates a quantum jump in the nuclei. In the first experiment, this was a special quantum state in nuclei of iron atoms. The second pulse is much longer and has an energy that is precisely tuned to the quantum jump. In this way, it can specifically manipulate the quantum dynamics triggered by pulse 1. The time span between the two pulses can be adjusted. This allows the team to adjust whether the second pulse is more constructive or destructive for the quantum state. Pulse control accurate to a few zeptoseconds, but what sounds simple is a technical challenge that required years of research. A controlled change in the quantum dynamics of an atomic nucleus requires that the delay of the second pulse is stable on the unimaginably short time scale of a few zeptoseconds. Because only then do the two pulses work together in a controlling way. A zeptosecond is 1/trillionth of a billionth of a second, or a decimal point followed by 20 zeros and a 1. The sample is shifted by 45 trillionths of a meter. The second X-ray pulse is delayed by a tiny displacement of the first sample, also containing iron nuclei with the appropriate. This corresponds to about 45 trillionths of a meter. After this tiny movement, the sample emits the second pulse. The physicists compare their experiment to two tuning forks that are at The bang first strikes the closer tuning fork, making it vibrate, and then moves on to the second tuning fork. In the meantime, the first tuning fork, now excited, emits sound waves itself, which arrive with a delay at the second fork. Depending on the delay time, this sound either amplifies or dampens the vibrations of the second fork, just like the second push on the oscillating swing, as well as for the case of the excited. With this experiment, Jörg Evers, Christoph Keitel, and Thomas Pfeiffer and their team from the Max Planck Institute for Nuclear Physics in cooperation with researchers from DESY in Hamburg and the Helmholtz Institute, Friedrich Schiller University in Jena succeeded for the first time in demonstrati. In addition to synchrotron facilities such as those at the ESRF, free electron lasers (FELS) such as the European XFEL at DESY have recently provided powerful sources. This opens up a dynamic future for the emerging field of nuclear quantum optics. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.